Hello, Mr. Claudia here. Today we're going to start looking at one of the principal applications of calculus, which is related to motion. Now, in the next three sections, we're going to look at velocity, acceleration, and finally distance traveled, and see how each of them relates to the derivatives and eventually the integral. If you studied physics before, some of this might seem like review, some of the concepts might seem like review because you cover a lot of these concepts in physics, but you'll find that some of the way we come about the solutions is different. We use calculus instead of the formulas that you use in physics class. So all of the examples we're going to be doing over the next 3 days are looking at motion in a line. There's two ways we look at motion in a line. We can look at it horizontally. So for example, you have, you're walking side to side, forwards, backwards, left, right. And this is the origin. This is 0. And this is S. And this is negative S. Or this is forwards. This is backwards. An example would be a car driving. I'll explain a little bit more about this in a minute. The other situation we're going to look at is vertical motion. And so we have the plus S here, minus S, or up and down. The example in this case would be a ball falling. Okay, so just to explain a little bit more about this. Well, we can actually first talk about the displacement function. So displacement describes the position of an object based on a set origin point. You might also call this the position function. So when we talk about where something is, we always talk about its displacement in relation to some fixed starting point or fixed point, which we call the origin. We measure displacement with usually with the variable s. So you'd have s at t, s is your position as a function of time, or your displacement as a function of time. If you go to the right of the origin, or you're going forward, then that would be a positive displacement. If you're to the left of the origin, you're going backwards, or there's a negative displacement. Similarly, if we're looking at an up-down situation, if you throw a ball up, it's got a positive displacement. If your ball goes below the origin, then it's a negative displacement. And the origin is some fixed point that you define. If you're standing on top of a cliff, you might define origin as the point at the top of the cliff. If you're throwing the ball from the ground, you might define origin as your position, as the ground level. Just to explain displacement, because it is kind of a confusing idea, we don't really talk about distance, we talk about displacement. So these formulas that we're going to be looking at over the next few days, they work for displacement only. And people who've studied physics will have an idea of this. For example, if here's my my yellow highlighter, I'm going to call that the origin. So if I put my, what is this guy? Little moose here. So right now he's positive 3 meters. He's 3 meters or 3 centimeters to forwards or to the right of the origin. If I were to put him over here, he's negative 1 meter. He's 1 meter to the left of the origin. Again, so that's kind of showing you the same thing here. I can be at the origin, so I'm at 0. This would be s equals 2, say, and this would be s equals negative 1 or something like that. So hopefully that helps. That's something we're going to have to get used to. We have s is greater than 0, s is less than 0. So actually, if we go back to my little guy here, if I have this function here which shows you the displacement as a function of time, right? S is changing as a function of time. So the moose or whatever starts here, and then as time goes on, he's moving down. And so that's what this function shows us. So for s at t, there's the function, s is in meters. What is the displacement at time equals to 2? Well, that's pretty easy. I sub in t equals 2. So I get s at 2 is equal to negative 4.92 squared plus 4.92 plus 10. I need my calculator for these because it's difficult to do in your head. So I have 4 times negative 4.9 times 4 plus 9.8 plus 10. And I get 0.2. So just to be clear, that means at time 2, the position is plus 0.2. So that means you're just, in this case, we'll say that this is left or up or down. It's hard to know what it is in this question. But we'll say the object is 0.2 meters above the origin. So I should say that this is a vertical one. That was something I forgot to type up. So in this case, the object is 0.2 meters above the origin. I don't know what happens later, but I know that when I sub in a time, it'll spit out the position with respect to the origin. Okay. The initial position is the position of the object when t equals 0. So if I want to find out where the object starts, I sub in t equals 0. So sub in t equals 0. So I have s at 0 is equal to negative 4.90 squared plus 4.9 times 0 plus 10. So that gives me 10 meters. So this tells me the object starts 10 meters above the origin. So if I wanted to map this out now, I have a better idea of things using my my very technical moose situation here. So the moose starts way up here, and then over 2 seconds, 2 seconds later, we know it's around here. So you know the motion is going to be something like that. But all we know right now is the starting point and what happens at 2 seconds. You'd have to sub in a lot of different numbers to figure out exactly where the moose was at every point in between. So that is position. I call it position, but in the textbook, and I teach it in physics as position, but the textbook calls this the displacement function. Okay, so now let's talk about what our lesson today is on, which is velocity. Velocity is the instantaneous rate of change of displacement. That is, it's the rate at which we change position. And it's no surprise, especially after talking about rates of change yesterday, velocity, which is marked with a v, is the derivative of position, or the derivative of displacement. Now, think about what this means. If your displacement is greater than 0, if you have a positive, if your velocity is greater than 0, then your object is moving forwards. It's moving to the right, or it's moving up. If your velocity is less than 0, the object is moving to the left, or it's down. And if your velocity is 0, the object is stationary. All right, so you can kind of imagine that, right? If I have my kind of friend of the moose here, my lion, if he's moving this way, his position is becoming more positive. So it's an increasing function, velocity is greater than 0. If he's moving this way, well, his displacement or his position is becoming more negative, so he's moving to the left. He's moving, and then his velocity is negative. And if he's not moving at all, then we know that the rate of change is 0. The units of velocity are meters per second often. Which you also might see, especially in IB, they like to write it like this. ms-1. The s-1, remember, it means 1 over s, so it just means meters per second, or meters over second. Or the one you're probably more familiar with is kilometers per hour. Which is also written as kmh-1. Now, you might be thinking, okay, I've heard of this. Like, the rate of change of position or displacement is speed. So what is speed? Why are we talking about velocity? Well, and again, if you've taken physics, you'll be familiar with this question. Speed is the absolute value of velocity. So velocity tells us how fast an object is moving and whether it's moving to the right or left. We just talked about that. You can have a positive velocity or a negative velocity. This has two pieces of information, a number and a direction. Speed is just a number. It only tells you how fast you're moving. So, for example, when you look at your speedometer on your car and it says you're going 50, that could mean 50 kilometers per hour forward or 50 kilometers per hour backwards. You don't really know. Hopefully you're not going 50 kilometers per hour backwards. But the speed is only a number. Whereas velocity, well, you could have plus 50, which means you're moving 50 kilometers per hour forward, or negative 50, which means you're moving 50 kilometers per hour backwards. So we often are talking about velocity with these formulas, but if someone asks you for speed, you just take the absolute value of velocity. You just take the numerical part. Okay, let's tourner la page and do a long example. Okay, a particle moves in a straight line with a displacement function given by like this, where t is the time, s is the displacement. So imagine this particle moving left or right. We don't know, but it's moving somehow. Okay, part A. And usually these questions start off the same way and then they get more difficult. So find the displacement of the particle when t equals 4. Well, this is my displacement function. So that means I just have to sub in t equals 4 because displacement, I just can read it right off of this equation. So I have s at 4 is equal to 4 cubed minus 15 4 squared plus 63 times 4. Again, these real life questions that have difficult numbers, you will always have a calculator to help you. And I got 76. It's a positive number. That means the particle starts off to the right of the origin, 76 meters. Again, it's weird for those of you who've taken physics. Displacement it means something different to me. I would call this position, but the displacement is the word you're going to see in IB terminology. Part B. Find the velocity of the particle when t equals 4. Well, the whole point of this lesson is velocity, and we know that velocity is the derivative of position. So let me just write out position. T cubed minus 15t squared plus 63t. So v at t is equal to the derivative of s. So that's 3t squared minus 30t plus 63. Good thing we know how to find derivatives. So now I have the velocity function. I want to find the velocity when t equals 4. So now I just sub in t equals 4. So v at 4 is equal to 4 squared minus 30 times 4 plus 63. So that's 3 times 16 minus 30 times 4 plus 63. That gives me negative 9. What are the units again of velocity? Well, remember, velocity is a rate of change. So it would be meters divided by time, so meters per second. Okay, let's keep going. So now we know actually at time equals 4, the particle is 76 meters to the right of the origin, but what's the particle doing? It's moving to the left, right? Negative, the speed or velocity is negative. It's moving to the left at 9 meters per second. Okay, part C. Hence, remember that keyword hence? It means use your answer from above. Write down the speed of the particle when t equals 4. Well, that's easy for us, right? We know the speed is 9 meters per second. The speed is just the absolute value of this. So it's just a positive, the numerical value from part B. Part D. Find the initial position and initial velocity of the particle. Well, we know when we see for initial position, think about if you're starting a race, your initial position is before the clock starts. So your initial position is t equals 0. Okay. actually, I'm going to write for initial position, we sub t equals 0 into s at t. So I have s at 0 is equal to 0 cubed minus 15, 0 squared, plus 63 times 0. So in this case, my initial position is 0. Now, for my initial velocity, same strategy, except I'm going to sub t equals 0 this time into the v at t function. So I have v at 0, and I have this function up here. So it's 3, 0 squared minus 30 times 0 plus 63. It's pretty simple. 0 plus 0. Okay, so this becomes 63 meters per second. So just to summarize what we learned here, at the start, the particle is at the origin and moving 63 meters per second to the right because it's a positive number. So far so good? Okay, let's continue. I think we'll fit the next question up here. Part E. Find when the particle is at rest. Okay, so we have to think a little bit. The particle is at rest, it's not moving. Well, for something to not be moving, we know that the velocity has to be 0. See, we're just manipulating these two formulas. So where is my velocity formula? It's right there. So I have 0 is equal to 3t squared minus 30t plus 63. Oh, that's just a quadratic. And to solve a quadratic, I need to factor this expression on the right. Let's see if I can still factor. First of all, I'm going to factor out the 3 to make the numbers easier. Oops, this is 21 actually, I believe, right? Oh, very messy. Okay, so 21. Okay, so now I think I can factor this. This is going to be, what's 21? 7 times 3? Yeah, minus 3 and minus 7, right? So I have two solutions then. T equals 3, the particle is at rest, and t equals 7, the particle is at rest. So we're learning more and more about what's happening with this particle. Okay, I'm going to use a new sheet of paper for the next question. Maybe you can try to cram it in if you're really daring. Let's go on to question F. So this is, what is this, 9.2a? Page 3. Okay, here we go. So part F. Okay. Find when the particle is moving left and right. So here we have to think a little bit. The particle is moving to the left. If you're moving to the left, is this talking about displacement or velocity? Well, the displacement just tells you where you are. If I want to know what direction you're moving, I actually have to look at the velocity. If you're moving to the right, velocity is positive. If you're moving to the left, velocity is negative. In other words, I have to find out when this function is positive or negative. I have to find when this function is increasing or decreasing. So really, this is just similar to what you did in the last chapter when we did curve sketching. If the velocity is greater than 0, then the object moves right. If the velocity is less than 0, then the object or particle moves to the left. So therefore, we need a sign diagram to analyze the sign of vt is equal to, and we factor that, so I'm going to write it in factored form, because we know that's what you need to do anyways when you're doing a sign diagram. Okay, so we need to basically go back to our notes from curve sketching. We need a sign diagram for this. If you remember, I'll just draw what I normally did. I usually made my sign diagram above, so I have sign diagram like this. Now, unfortunately, for this sign diagram, you can't have negative time, so this is the sign of vt, and this is t. And you can't have a negative time, so we start with 0, and then we have a critical point at 3, and we have a critical point at 7. So we're going to have to look at these 3 intervals. So let me make my sign diagram below it. So I have one, two. So I have t is between 0 and 3. I have t is between 0 and 7, or 3 and 7, and then I have t greater than 7. And my factors are 3, t minus 3, t minus 7. And so I'm just going to show the full table like that. Hopefully you guys remember how to do this. If you're unsure, go back to your previous chapter's notes. Okay, so choose at 3. Well, 3 is always going to be positive no matter which of these sections I'm looking at. Okay, what about a number between 0 and 3? So say 1, well, that's going to be negative here. This is going to be negative here. What about if I choose a number between 3 and 7? Okay, say 5. So 5 minus 3 is positive. 5 minus 7 is negative. Finally, if I choose a number greater than 7, say 8, I get a positive and a positive. Well, positive times negative is positive times positive. Positive times negative, and this is positive. So, what does this tell us? Well, it tells us that between 0 and 3, the sign is positive, then negative, then positive. Now, the question was, when is velocity positive? When is it going to the right? Well, that would be from 0 to 3 and from 7 onwards. So, therefore, the object moves right when t is between 0 and 3, and when t is greater than 7, and the object moves left for t is between 3 and 7. Great. Again, just an application of what we did in the last chapter, but now in a real life situation. Okay, finally, the last question, draw a motion diagram for this particle. So we have to kind of unravel exactly what's happening. And now, by this point, we know quite a bit of what's happening. The object starts off where? At the origin, then it moves to the right, then for 3 seconds, then it moves to the left for 4 seconds, and then it moves to the right forever. So let's draw what we know then. Okay, let me get a ruler out. So it starts off here. And of course, I can't show the particle going back and forth, back and forth, back and forth. So I try to show when it turns, it goes up slightly, but it's still just going back and forth. It's only along a line. So we know at the beginning the particle moves to the right. That's what we just figured out. And you know, at this point, the beginning, we've already figured out. I'm just going to put a little line here. This will show my passage of time. Or no, this will show me positive s. So we know at t equals 0, we know that s equals 0. Okay, now we know that at t equals 3, the particle stops. Remember, we figured out that at t equals 3, that was a previous question. We know the particle is at rest at t equals 3. So the particle stops, and then it turns around. And we know then that the particle is moving left for a little bit. Well, I wonder how far. So we have this arrow kind of showing the particles moving, and then it turns and is moving the other direction. Okay, now at t equals 7, it's going to turn again, and it's going to be moving to the right again. However, I don't think I know what it's doing at t equals 4. I don't exactly know where it is at t equals 3. So let me just figure some things out. So find, oops, sorry. I just need to know some of these positions. So find the position of the particle when it changes direction. So S at 3, at this point, what is the position? Well, S at 3 is equal to, I'm going to sub this into my function, so it's 3 cubed minus 15 times 3 squared plus 63 times 3. Let me just do the math here. So that's 3 to the power of 3 minus 15 times 9 plus 63 times 3. That gives me positive 81. So I know that at time equals 3, I'm 81 meters to the right when I turn around. Now, I'm heading backwards. What happens at t equals 7? Well, he turns again. But I should figure out where I am at that point. So at t equals 7, I have 7 cubed minus 15, 7 squared, plus 63 times 7. Let me just do the math on that. So I have 7 to the power of 3, minus 15 times 7 squared, plus 63 times 7. Let's see if I get the right answer. Hopefully that's it, 49. So now, okay, at time equals 3, I was 81 meters to the right of the origin. There's the origin there. Now, at time equals 7, I was 49 meters. So I was kind of like halfway. It was somewhere around here. Oh, somewhere there. So this is at time equals 7. My position is 49, right? That's my new position with respect to the origin. It's not how far I've traveled. It's my position. Okay, and this was, it was moving left here. And then it turns around, and from there we know from the last example up here it's moving now to the right forever. So there you have your motion diagram. Particle starts at the origin, moves to the right. At 3 seconds and 81 meters away, it turns backwards, and then at 49 meters away after 7 seconds, it then turns again and keeps going forever to the right. Beautiful motion diagram. Leading us to our final question. Use the motion diagram to determine the total distance traveled. Well, this is actually pretty straightforward if you have your diagram made nicely. So at the beginning, we travel how far? 81 meters. Then it travels another, whatever this distance is. And, oh, the question only wants actually the distance traveled between 0 and 7 seconds. So you can see that the particle, to find the distance, we add the distances traveled. Think about distance. It is also a number, just a number. It doesn't have anything to do with position. It just wants to know how far you've walked. So at the beginning, the first 3 seconds, we've gone 81 meters. And then we went, whatever the distance here, 81 to 49. So what's that? Well, we can figure that out. That's 32. 81 minus 49. So just to be clear what's happening here, this is the distance traveled between 0 and 3. This is the distance traveled between 3 and 7. So that gives me 162 minus 49 is 113 meters. Just to be clear, distance has no direction. It's just a number. It's just how far you've walked. So we walked, was it 81 that way, and then whatever it was, 32 that way. Great. Okay, so that is everything you need to know about displacement and velocity. Note that it's just an application of rates of change, and if you're careful and you don't get confused between the two functions, you should be fine. Your homework for this section is a sheet that's attached, and it is number 1, 3 to 6, and 8 to 9. Good luck with that, and we'll see you next time.